In this video, I'm going to prove the Rolle theorem, which says if a function is continuous over closed interval a, b, and differentiable over this open interval, and if the functional values are equal to each other at both edges, then there exists some constant inside this open interval so that the derivative at this point is equal to exactly 0. So graphically speaking, it's very clear. So this is A, this is B. Functional value are exactly the same at those points. Right? Then, of course, there must be at least one point where at this point we have the derivative is equal to 0. For example, this point, right, it's a local maximum. At this point, the derivative is clearly 0, but we're going to have to prove it rigorously. But before that, we have to prove Fermat theorem, Fermat lemma, which says that if the derivative exists at x0, and fx0 happens to be the local extremum, local minimum, local maximum, whatever, then we can conclude that the derivative at this point has to be 0. Then we're going to use that to prove the Rolle's theorem. So first of all, graphically speaking, even though graph is not part of the proof, but it can help us to demonstrate it more clearly. So let's say if we have the graph of this function looks like something like this, and let's say at x0, the function takes the local minimum, right? So local minimum f. And since the derivative exists, which means the derivative is equal to each other at the left-hand side derivative and the right-hand side derivative. But before we do that, we say it's local extreme, local minimum, which means there exists a small enough. May not be a big interval, but maybe a small neighborhood, right? This neighborhood, the delta. x0 plus delta and x0 minus delta, inside this neighborhood, functional value is the minimum at this point. In other words, there exists delta, so that when x lives inside the open interval of x0 minus delta and x0 plus delta, as long as x lives in this neighborhood, open neighborhood, then we always have f of x is always no less than f of x0. So from the right-hand side, right, so this is x0 plus delta, this is x0 minus delta. Right? If we approach from the right-hand side, right, if x lives inside this half of the open interval, then it's the same thing. F of x minus f of x0 is clearly non-negative, right? Since f of x is already the local minimum. And plus, we also have x minus x0. Since x is approaching from the right-hand side, right, inside this, so x must be greater than x0, right? So the bottom also is positive, right? So overall, the whole thing is positive. So if we take the limit, we let x approach x0 from the right-hand side, right? Limit should also exist, should also be greater than or equal to 0, because it says the derivative exists, right? So therefore this exists as well. Likewise, if we let x lives in this left-hand side open interval, then we can say f of x minus f of x0 still non-negative, right? Because functional value at x0 is already the local minimum. Right? And if we divide by x minus x naught, remember, at the left-hand side neighborhood, right? X is minus x naught has to be negative. Right? Negative. So therefore, the whole thing has to be less than or equal to 0, right? Positive over negative. If we take the limit, we let x approach x naught from the left-hand side. Like for the same reason, right? The left-hand side derivative exists because the derivative is given to exists, right? So we have the right-hand side derivative is equal to the left-hand side derivative, right? Because derivative exists. Then, so therefore, at the same time, it has to be non-negative. At the same time, it has to be non-positive. So therefore, it has to equal to 0, right? So this is in fact derivative itself, also derivative itself. So derivative itself as a constant is at the same time less than or equal to 0, at the same time larger than or equal to 0. So we conclude the derivative at x naught has no choice but to equal to 0. But from the graph, it's very intuitively clear, right? Because how else could it be? It has to be a flat line. The tangent line has to be flat, right? Equal to 0. Now I've proven Fermat's theorem. Now the proof of the Rolle theorem is very simple. So first, special case. Because function is continuous everywhere on this closed interval, therefore the function has to be uniformly continuous, right? Uniformly continuous, therefore the function takes global maximum and global minimum. Right? So local extremum does not imply global maximum or minimum, but global maximum and minimum has to imply local minimum and local maximum. So in that case, let's just denote global maximum as big M and global minimum as small m, right? In the case of let's just denote f of A and f of B as a constant C, right? In the case of if both global maximum and global minimum can only be taken at A and B, right? In that case, right, this is FA, FB equal to C. In that case, so global maximum is equal to C, right? And global minimum is equal to C. Global minimum equal to C. In that case, the function is clearly a constant function. Right? It's very clear. Right? Global minimum, global maximum. Right? Function cannot equal. Is no larger than C, no less than C. Has to equal to C always. In that case, it's a. Do we have a point in the open interval whose derivative happens to be 0? I say obviously yes, because it's already a flat line. So every point has the property that its derivative is exactly 0. That's very clear. Now, in the case of if at least one of the global maximum and global minimum can be taken in the open interval, excluding both edges. In that case, what will happen? In that case, like I said, since global For example, global minimum indicates local minimum. Since it's local minimum, so M local minimum. Then according to Fermat, with local extremum, if the derivative exists, does the derivative exist? We're given that its derivative always exists inside the open interval. Then we can say, according to Fermat, the derivative at this point has to equal to 0, right? So in this case, M is taken at f of c, right? Right, somewhere, c is somewhere in the open interval, right? Somewhere in the open interval. For example, this is c. Right? So that if the derivative at c is exactly equal to 0. So now so from the graph it's clearly, right, intuitively clear. At this point, since it's local minimum, the tangent line has to be flat. In other words, the derivative has to be 0. Now, in the future, I will use the Rolle theorem to prove Lagrange mean value theorem in terms of in the context of derivatives, and also Cauchy mean value theorem, and also Taylor expansion with Lagrange remainder and Cauchy remainder. I've already proven in the previous video about Taylor expansion with Peano remainder, right? Peano remainder. And in that video, the usefulness of Taylor expansion with Peano remainder is that it's very useful when calculating limits, because through the Peano remainder we obtained a very, very precise approximation nearby some point x0, where we can precisely approximate the function using Taylor series. But with the Peano remainder, we don't have exactly the properties over a global context. In a global context, right? We only know its property nearby x0. It's a local concept, right? Local context. It's only useful when we're in the nearby neighborhood of x0. But we don't know the detailed properties over a longer interval, over interval AB. Right? We want to know its property over AB entirely, global property, right? Instead of just knowing the properties just nearby x0, right? In a very, very small open interval, right? We want to know its global property over the entire AB interval, right? That's when we introduce Cauchy remainder and Lagrange remainder in Taylor expansion. I will prove it in a future video using Rolle's theorem.